A differential pressure (DP) flow meter is a common device. It measures how much fluid moves through a pipe. It works by sensing a pressure difference. This pressure difference is created by an element in the flow path. This element is called the primary element. Common types of primary elements include orifice plates. Venturi tubes and flow nozzles are also widely used. These elements all function by creating a predictable pressure drop. The meter then relates this drop to the flow rate. The principle behind a DP flow meter is quite straightforward. The primary element causes a slight constriction in the pipe. As the fluid passes through this narrower section, its speed increases. This increase in speed leads to a decrease in pressure. The meter measures the pressure before the constriction. It also measures the pressure at the narrowest point or slightly downstream. The difference between these two pressures is the differential pressure. A higher flow rate will generally produce a larger differential pressure. This relationship is based on fundamental fluid dynamics principles. DP flow meters are utilized across a vast range of industries. You will find them in oil and gas operations. They measure crude oil, natural gas, and refined products. Water and wastewater treatment plants use them extensively. They monitor water distribution and effluent discharge. The chemical processing industry relies on DP meters. They control the flow of various chemical ingredients. Even heating, ventilation, and air conditioning (HVAC) systems in buildings employ DP flow meters. They help manage air and water flow for climate control. Their versatility makes them a popular choice. While DP flow meters are very useful and widely adopted, they are not infallible. Sometimes they can provide readings that are incorrect. Specifically, they might indicate a flow rate that is higher than the actual flow. This can lead to operational problems or inefficiencies. Understanding the reasons for such erroneous high readings is crucial. It allows operators and technicians to troubleshoot effectively. This essay will explore common causes for these high flow reading errors. We will look at blockages, calibration issues, and temperature effects. Blockages in the pipe can cause a DP flow meter to read high. A blockage restricts the normal flow path of the fluid. This restriction can occur upstream of the primary element. It can also happen within the primary element itself. For example, an orifice plate can become partially clogged. The increased restriction caused by the blockage leads to a larger pressure drop across the measurement points. The DP transmitter senses this artificially increased differential pressure. It then incorrectly interprets this as a higher fluid flow rate. This is a frequent source of error. Several types of obstructions can lead to these false high readings. Solid debris carried by the fluid is a common culprit. This could be dirt, rust particles, or small pieces of sediment. In some processes, scale can build up on the inner surfaces of the pipe. This scale can also accumulate on the primary flow element. This gradually reduces the open area for flow. Another less obvious blockage can be a partially closed valve. If a valve upstream of the meter is not fully open and this isn't known, it acts as an unintended restriction. This also creates an additional pressure drop. Consider a real-life example in a paper manufacturing plant. The process involves pumping paper pulp, which contains fibers. Over time, these fibers can accumulate on the upstream face of an orifice plate. This buildup effectively reduces the orifice bore diameter. The actual flow of pulp might be decreasing due to the blockage. However, the DP flow meter will register an increased pressure drop. It will therefore report a higher flow rate. Plant operators, seeing this high reading, might mistakenly reduce pump speed. This action would further starve the process of necessary pulp. To prevent and address issues caused by blockages, several practical steps can be taken. Regular inspection of the primary flow element is essential. This includes checking for any signs of wear, damage, or buildup. A consistent cleaning schedule should be implemented, especially for fluids known to contain solids. Installing filters or strainers upstream of the flow meter can capture debris. This prevents it from reaching the primary element. Careful selection of materials for the pipe and primary element can also help. Choosing materials resistant to corrosion or scale formation for the specific fluid can minimize buildup. Incorrect calibration of the DP transmitter is a significant reason for high flow readings. The transmitter is the electronic part of the meter. It converts the measured differential pressure into an electrical signal. This signal then corresponds to a flow rate. This conversion relies on accurate calibration. If the relationship between pressure and flow is set incorrectly during calibration, all subsequent readings will be skewed. For instance, a zero shift, where the transmitter reads a pressure even with no flow, can cause high readings. Similarly, an incorrect span setting, which defines the range, can also lead to errors. Correcting calibration errors requires a methodical approach. Regular calibration checks are fundamental to maintaining accuracy. These checks should be performed against a known and reliable reference standard. It is important to use certified calibration equipment for this purpose. All calibration activities, including adjustments made, should be thoroughly documented. This creates a history for the instrument. Critically, the transmitter should be calibrated under conditions that reflect its actual operation. This includes the expected range of pressures and, importantly, ambient temperatures. Proper calibration ensures the transmitter accurately reports the flow. Temperature variations can also significantly impact the accuracy of DP flow meter readings. The density of most fluids changes with temperature. Liquids generally become less dense as they get hotter. Gases are even more sensitive to temperature changes. DP flow meters often use a fixed density value in their flow calculation. This density is typically based on an assumed or calibrated operating temperature. If the actual process fluid temperature deviates substantially from this assumed value, the fixed density value becomes incorrect. This leads to an error in the calculated flow rate. When temperature changes are not properly accounted for, high readings can occur. For example, if a liquid is hotter than the temperature for which the meter was calibrated, its density will be lower. The DP flow calculation, if not compensated for this lower density, might interpret the measured pressure drop as representing a higher volumetric flow. While the relationship is complex, the key is that an uncompensated density change leads to error. Many modern DP transmitters can accept a temperature input for dynamic density compensation. If this compensation system fails, is misconfigured, or is not present, significant temperature-induced errors, including high readings, can result. Let us consider a real-world example of a calibration error causing high readings. Imagine a steam flow meter in a power plant. This meter measures the amount of steam going to a turbine. Suppose the DP transmitter was last calibrated during a warm summer month. The ambient temperature around the transmitter was high. Later, during a cold winter period, the uninsulated transmitter body cools significantly. This temperature change can affect the transmitter's electronic components. This might cause a drift in its calibration, leading it to output a higher signal for the same differential pressure. The control system then shows an inflated steam flow reading. Another practical example involves temperature variations in a hot oil heating system. Such systems are common in manufacturing. The oil is heated and circulated to transfer heat to various processes. The temperature of this oil can fluctuate depending on the heating demand. If the DP flow meter measuring the oil flow is calibrated for an average oil temperature, problems arise. When the oil becomes significantly hotter than this average, its density decreases. Without dynamic temperature compensation, the flow meter will still use the old higher density value. This mismatch in calculation will result in the meter reporting a flow rate that is erroneously high. Several proactive measures can help avoid these misleading high flow readings. Implementing a comprehensive and regular maintenance schedule is paramount. This schedule should include inspections, cleaning of primary elements, and routine calibration checks. Thoroughly training plant personnel is also crucial. Operators and technicians should understand the operating principles of DP flow meters. They need to be able to recognize symptoms of potential problems. Many modern DP transmitters are equipped with advanced diagnostic features. Utilizing these features can help detect issues like sensor drift or blockages early. Consider using multivariable transmitters where appropriate. These measure DP, static pressure, and temperature simultaneously for better accuracy. In summary, DP flow meters are valuable instruments for industrial process control. However, it is important to be aware that they can sometimes indicate falsely high flow rates. The most common culprits behind these errors are physical blockages in the flow path. Incorrect calibration of the DP transmitter is another major factor. Finally, uncompensated variations in fluid temperature can significantly affect density and, consequently, the flow reading. By understanding these potential causes, and by implementing diligent maintenance and calibration practices, users can ensure their DP flow meters provide reliable and accurate data for efficient and safe operations.